I'll edit the video later. Okay, so for this inductor problem, it is even more essential to draw a Thevenin equivalent circuit for whatever it is that I'm looking at. This thing was initially shut, so its initial was with a charge right here, right? Because this 200 volt was plugged into the circuit, and so it initially had a charge. Well, in its final state, it looks like this over here on the right that I'm highlighting. In its final state, it wasn't plugged in because it was open, right? The switch opens at t equals 0. And so whenever I'm looking at, oh, nuts. There we go. So whenever I'm looking at this, I can just visually see that it is 0. This is why I say it's helpful to redraw. You don't have to. I can probably see this one okay without needing to redraw that. But you can clearly see it right here is that this is, I said it's like a portable phone charger, if you will, that's plugged in to the wall initially. Then I unplug it from the wall and it's plugged into my phone, right? You can plug in a portable phone charger after it's received a charge. So it received a charge, it dissipated the charge into my phone. That's an analogy I find helpful, right? So now it's charging down to 0. So that's what this equation is saying. That as a function of time, what is the charge, right? What is the charge by looking at what is the current? So I'm looking at the current. Well, initially, it had a charge, it had a current. Then it went down this transient equation to another steady state. And this final steady state, in this case, was 0. So this is discharging from something down to something. Okay, so I final is 0. So now we're going to determine the initial voltage across, and that induced, and wait, that's sketchy. The initial voltage. This is, man, if y'all were trying to solve this one, because like normally we solve the current and then the voltage, which is fine, but it's an extra step that I didn't realize I'd put in that problem. So that one probably is challenging. Did anybody solve for that one? Anybody get to that one, or is most everyone just work on the capacitor? Sounds like everyone's working on the capacitor. Okay. So the initial voltage is what it's asking for, but in order to do that, we're going to do the current. And the way that we're going to do that is we're going to look at the circuit as a Thevenin circuit. The reason why is because I would have to do a current divider rule to find this current going through here. So it's might as well, because I'm going to need the R Thevenin anyway, might as well find the E Thevenin and make my life easy. So if I'm looking at this E Thevenin circuit, right, the E Thevenin circuit that I'm going to draw looks like this. And I'm looking for E Thevenin right here. Well, in this case, I can see this thing is dead. This one in the green, that one's dead because once I've opened it up to do the Thevenin, all that's left is this. So all my E Thevenin is equal to 200 volts. Now I'll do the R Thevenin. Whenever I short that circuit or short that voltage source, it's the same thing that I had before where I'm looking at it. Whenever I'm doing these Thevenins, I'm looking at it from here. So it goes through that one, which was 50. So 50, this one's 500. So I'm looking at it as the green dots. That's what I'm looking at, right? So R Thevenin, looking back from here, is initially 50. Everyone okay with that? But that's all that it is, because if I follow this circuit along, it doesn't divide. It takes the path of least resistance, and all of it goes this way. It bypasses the 50, the 500. So now I have here, there's the redrawn Thevenin circuit, 200 volts, 50 ohms. That should be a 0. Got messy. 200 volts, 50 ohms. Well, what happens when it's fully charged, which is what this case is? It's a wire. So here's 200, here's 50. What is the current going through that? Just V over R, 200 over 50, 4 amps. So that's the way to do it with the Thevenin. If you were doing a current divider rule, I could just redo it. So with CDR, this is a different way to solve it. But I have my voltage source here. It goes like this. There's the other resistor, and then here's right through there is IL. So when I'm looking at this IL, it's a wire because it's a fully charged inductor, and so 200 volts is going, and it's splitting, and I'll draw these in green. It's splitting this way and this way. So how is it splitting? Actually, I'm not even going to do it with a current divider. I'm just going to do it with Ohm's law, because that's another way to do it. With Ohm's law, which is that it's between these two nodes. The voltage 200 volts is the voltage across that same 50 ohm. So with Ohm's law, it's the same thing. V over R, 200 volts on the outside of that node, and I need to know the current going through it, and it's another 50. You could do it with CDR, which in this case would be 50 paralleled with 500. I'm looking through the branch that is 50, and then the current being split up. This is where it gets messy because that I total is what would go in here. And the I total is the 200 volts divided by 50 paralleled with 500. So like I said, this is probably, if you're getting confused now, then just take a deep breath, because this is just 3 different ways to get the same thing, which at the end of the day is giving me 4 amps. I'm just trying to show there's different ways to solve it, but the Thevenin one, I think, is the easiest one because it works every time, whereas it doesn't require a different tool, right? Current divider, Ohm's law. It is good for your brain if you can do all of them, but if you're looking for just what do I do when I see an inductor in transient, I do a Thevenin equivalent. Does that make sense? So that's why I'm emphasizing that one. It's the go-to because it always works. The other ones will work, they just require more thought, and sometimes that can mean more time. Okay, I think that's, let me just, so the last part that I just want to say, because I realize that we haven't quite finished this equation, is this tau. So this tau that is consisting of L over R, and this is the R Thevenin. This is the R Thevenin of the final, okay, of the final circuit, which in this case, here's my final circuit, right? And that's the case in the other one. The R Thevenin is of the final circuit. Well, what is my Thevenin equivalent of these two? It's just 5 or 50 plus 500, which equals 550. So if I plug that in, L is 100 millihenries. R is the final Thevenin is 550. And that comes out to 909 microseconds. So I'll write in everything right here. Here's my final equation. Inside of here, I, the current going through the inductor, I final, we said was 0. Plus I initial, we said was 4 amps, minus 0, e to the negative t over 909 microseconds. So if I'm simplifying the equation, IL is equal to 4 amps e to the negative t over 909 milliseconds.